All right, let's look at another application with graphs of fundamental theorem. So we can see we have a function, capital F of x equal to an integral under this graph of f of t over here. And it's from 0 to some x value on this graph that's not given. One important thing is this is a continuous function which we need in order to apply fundamental theorem here. So what they want us to find is what is capital F at 1, 2, 3, 4, 5, and 6 here. So we want to find out what those values are. So if we want, we could set up like a little table here where x is our input, f of x is our output. If we find this first one at 1, that's the amount of area then from 0 to 1 on this graph, because if we're putting 1 in here, it's an integral, and integrals find the area underneath the graph. So that would be 2 square units of area. The next one, if we now find it 2 at 2, so now our new input here, we'd be finding capital F of 2, so it's the amount of area from 2 to 0. So now we're adding this additional area here. That's adding 2 more full squares plus half of 2 squares, so that's adding another 3, so now we are up to 5. And we can continue doing that. Why don't you pause the video and see if you can come up with the rest of these values. All right, let's check out if you got them right here. Again, you're adding the additional area each time. If you didn't get this part, remember that the area here now we should start subtracting off that, because the height of these Riemann sums would be negative, and so it comes out to be a negative amount. So you should have seen a decrease in the values starting at 4 there. All right, nice. So let's continue then. The next one wants us to, for the same graph and function, identify the intervals where f of x is increasing and decreasing. Well, when we're looking at this, we can kind of go back to the points we had before here and estimate that. It looks like we were in our points kept increasing in here and then started decreasing in this next one. But we also know from fundamental theorem of calculus here that if we take the derivative of this side, we get the derivative of f. But that also means we need to take the derivative of the other side of this integral of function f of t dt. But from what we looked at in previous videos is that this then equals just f of x by fundamental theorem of calculus. So we know what the derivative of capital F is equal to. Well, we can use that to help us figure out increasing, decreasing here. Because remember, where your, if you have a derivative, that tells you slope. And so this graph is going to be increasing where the derivative is positive, bigger than 0. It's going to be decreasing anywhere our derivative is negative or less than 0. So we can find that out knowing that our derivative is the same as the graph that's shown in this picture up here. So what we want to do is figure out where is f prime greater than 0, but also we know that's equal to our function. Where's that greater than 0? And this we know from the picture. So what we can do, look at it, go to our picture and do is find where is this function going to have positive values. That would be right in here. So this graph's going to be increasing on the interval from 0 to looks like 2, 3 here on the interval from 0 to 3, because that's where f of x has positive points. So to figure out our decreasing, very similar, we want to find where's the derivative, negative or less than 0. But by fundamental theorem, we also know that's equal to f of x. Where's that less than 0? On our graph, we can see that that's right here. That's where we have negative points. And so that's going to be where this one is decreasing. It's going to be decreasing on the interval from 3 to 7. So that would be the points that we, that would be the places where it's decreasing. And that looks familiar to what we found here. Notice how these points were increasing here and then decreasing here, so we get the same thing as indicated on our ordered pairs. All right, next thing that they're asking to identify on this graph where f of x has the absolute max and absolute min. Okay, so again, going back to stuff we know, that would absolute max and mins occur at either endpoints or where the derivative equals 0. Well, by fundamental theorem of calculus that we just did, we know the derivative here is equal to f of x. So where's that going to be equal to 0? On this one, we don't really maybe know that, but from the graph here, we know this is going to be 0 right here. Also looks like it's 0 at 7. So at both points 3 and 7, this occur. So the points where this could be would be x equals 3 and x equals 7. But we also want to include any endpoints. F of 7 is an endpoint, but we should also check this other endpoint at 0. So those would be the 3 possible places then where this has an absolute max and min. So then to figure out which one's the max and min, figure out the y values that go with that, figure out what is f of 3 going to be equal to, what is f of 7 going to be equal to, what is f of 0 going to be equal to, and whatever the highest and lowest one, that would be our absolute max and min. We've found these values previously. Our f of 7 came out to be 2. Our f of 3 came out to be 7. F of 0, I think, was the only one maybe we didn't do. But if we have an interval or an integral from 0 to 0, that's accumulating 0 area. So that would be 0. So our absolute min would be at the end point of 0, because we're not accumulating any area yet. Our absolute max would occur at that where that derivative equaled 0 there at 3, x equals 3. So the max would be set at x equals 3. All right, last question they're asking on this. Identify the intervals where it's concave up, concave down. So again, let's apply what we know. We know that this graph will be concave up where the second derivative is positive. That's where it's going to be concave up, if you remember our little smiley face here. So this is where it's concave up. Where our second derivative is negative, that's where it's looking like this. That's where we're going to be concave down. So if we can figure out what we know about second derivative of this function, that we can use that. Well, we don't know what that f function looks like, but what we've done from previous other things they've asked already is that first derivative is equal to f of x by fundamental theorem of calculus. If we go one step further then and take the derivative of each side, that tells us the second derivative of this is equal to the first derivative of x. So when we're looking for this, even though we don't know anything about capital F of x necessarily, we do know that it's the same as f prime of x, the first derivative. So we're going to use the first derivative, or what we know of the first derivative from this picture, this graph here, to figure this out. So what we got to do is be able to interpret, what does this mean on the graph? On the graph, where the derivative is greater than 0 of this graph, we know first derivative talks about slope. And so anywhere where the slope is greater than 0, positive, that should be where this is concave up. I see two intervals where that happens. One right here, so from 1 to 2. Also, I see another one over here, so from 6 to 7. The interval where this is going to be decreasing then is where our slope is less than 0. So on our graph, that's where it has negative slope. We see some intervals here where there's negative slope here and here. So we can just combine those together into one and say that it would be from 2 to 5. That's where it's going to be concave down.